Welcome everybody, and then thanks Georgi for inviting me here. I'm very excited to share some new stuff about NVCOMP, some old stuff as well. And so let's just get started. Yeah, a few words about myself. I've been with NVIDIA for about 13 years, I think, by now. And I started as a graphics engineer, and then I transitioned towards HPC, CUDA, DevTech, and then recently transitioned to a manager role in the same DevTech team. Yeah, my background is I work on accelerating and optimizing applications on the GPU, and my team works on many different types of applications, and starting from machine learning, deep learning, data analytics, databases, all enterprise applications. And okay. Yeah, so I think maybe about 4 or 5 years ago, I started working on, started looking at accelerating databases on the GPU. And as many of you probably know, databases are very memory intensive. There's not much compute happening on, like, for example, a matrix multiplication, you have the gems. They're pretty compute intensive, and databases, you're mostly just accessing memory, and you're kind of very memory intensive. And we're often limited by the random access performance in that case. And here I have a plot of comparing the latest CPUs and GPUs. So AMD EPYC with 8 memory channels, and NVIDIA A100, 40 gigabyte and 80 gigabyte board. And the gray bar here is a peak sequential bandwidth that we have. And then the green bar is a measured random 8-byte access. Essentially, you can see, like, either for sequential random access, the GPUs outperform CPUs by order of magnitude about 10x. And so GPUs was like, I guess pretty quickly we determined GPU is a good fit for databases if you can feed data, if you can feed the database in GPU memory. Obviously, GPU memory is limited in capacity. So what do you do when it's very large? So 2 years ago, I had a talk at ADMS workshop at VLDB, where I showed some performance results and projections for TPCH Query 4, running from GPU memory and from CPU memory. And here you can see the 2 lines here, the CPU memory performance and GPU memory performance. And I measure the results in bandwidth, so like gigabytes per second. And well, you can see, like, GPU performance was really nice, and it was also scaling from going from T4 GPU, let's say, to V100, because V100 has a higher memory throughput. But on starting from CPU memory, we're essentially just PCI-E bottleneck there. So the whole advantage that we have from using from fast random accesses to hash tables on the GPU, we don't see them, right? We're just limited by this narrow link from the CPU to the GPU. And if you move towards now, 2 years from 2019, we have now PCI Gen 4 supported on our GPUs, right? And we also have better HBM. So we have roughly 2x improvement in PCI-E and also random access performance. But the result is we're still PCI-E bound when we start from reading data from CPU memory. So how can we overcome this PCI bottleneck? And I think there's like a few approaches to that. The first option is you can have a fast interconnect between CPU and GPU, and there is a system like that with P9 and Volta connected over NVLink. And also here I'm showing highlighting a paper from Sigmod just last year that I think won the best paper award about the pump up the volume. So they showed how to leverage that system for databases, right? That's one approach how you can kind of improve performance if you just have better hardware, right? Like interconnect with CPU and GPU. And at this last GDC, we also announced a Grace CPU that's tightly coupled with GPU. So that's should be also a good step towards that direction. Another approach is you could have just more GPUs, right? And so typical system here is DGX. We have lots of GPUs, they all connected over multiple CPUs as well, and you can have a faster overall aggregated link to your memory. And you can also maybe split your data across many GPUs, and so that you have more overall GPU memory. So like if you look at DGX A100, it's a 640 gigabytes of GPU memory total there. And there's been quite some work on accelerating, using these systems for databases, some GDC talks, LDB talks, and so forth. And the third approach is compression. That's what we're going to talk about today. This the kind of a long introduction. I think I wanted to make kind of explain how we started and how we got to this point, and how I essentially got to working on NVCOMP and compression. So the first thing that I'm going to cover is whether GPUs are actually a good fit for compression or decompression algorithms. It's not going to be a very in-depth presentation, but I will highlight a few points there, a few kind of critical points. And then I think we talk about, so after covering this, I think we talk about NVCOMP as a library, some interfaces, performance results, use cases, and then we conclude and maybe move to questions. So there's lots of compression techniques out there, and I listed on the left kind of list of fundamental operations that people use. So for data deduplication, you could use dictionary compression, you can use LZ77 based compression, you can use RLE compression, run length encoding. Then the second family of compressors, if you can somehow encode the difference between. So the second family of compressors exploit the similarity between, maybe consequent numbers that you see, or maybe frames that follow each other, right, in a video sequence or something like that. So it's difference encoding, and there's a bunch of approaches there, including delta compression, frame of reference, and so forth. And then the third family is entropy encoding, right? So you're trying to store your data with less number of bits and kind of exploit, that more frequent numbers, or like more frequent elements you store with fewer bits as possible, right? So that way kind of we're all compressing your full sequence there. And the three methods I want to highlight is bit packing, Huffman, and NS. I think are pretty promising, all of them. So you can read about all these methods, and I have a more detailed presentation of the GDC. But essentially, these are the kind of fundamental operations. Then people and many common formats, they just combine these schemas together. So, for example, in deflate, you will have LZ77 based and Huffman used. So you kind of find the LZ matches first. So the way the compressor works, right? So it finds the LZ matches there, and then it stores the literals and the match copies with Huffman using Huffman trees there. And then another popular format is Z standard. It's also a combination of LZ77, Huffman, and also the asymmetric numerical system entropy encoding there. In addition to all these fundamental operations, many compressors, or like in the real world, you might see applications using some domain-specific techniques, right? A very common one listed, and I have an example here on the right, this picture. If you're trying to compress a bunch of, let's say, floating point numbers, normally, if you do like a delta compression, probably wouldn't give you good results, or RLE or something else. And so what people do, they first transpose the bits so that you have first store kind of, instead of storing the bits as they are, you store the first bit of every word, then you store the second bit of every word, then you store the third bit of every word, and so forth. And that way, maybe if your numbers have similar exponent, right, then you're probably going to have the same zeros, or like the same ones in the same places. And there's different variations for this bitplane transpose, but that's kind of the very basic idea there. And that way you transpose your data, and then it becomes more amenable to compression, such as RLE or some other techniques there. So often people kind of use this bit shuffle before the compression. And then you can also do sorting, pretty straightforward, kind of a similar approach. And then if you don't care about the ordering of the numbers, right, you might want to just sort them and compress. Or another very common transformation is WT Beres-Wheeler transform used for string compression. So the Beres-Wheeler transfer, for example, is used in the zip compressor. So I talked about all these different techniques, and when we started working on databases, compressors, we found that this particular cascaded compressor works very, very well. So it doesn't have any LZ in there, LZ77 based compression there. It just uses RLE and delta and bit packing. So it's pretty simple. And the idea was, okay, can we build a very simple, fast compressor, decompressor, right? But that's efficient on the database data sets. And I have a talk about that from 2020. It goes more in depth about the compressor itself, but the main idea, let's say you have a sequence of numbers, you apply RLE on top of that, you produce two arrays there, runs and values. Then for runs, you use something like frame of reference and bit packing. So you store, let's say, the minimum value, in this case 2, and then the bit pack all other numbers based on that. And then for values, you can apply something like, let's say, delta. So again, here you store, for delta, you store the first value and the differences between the consequent numbers there. And then again, on the, after that, you apply something like RLE, and you could further do the bit packing. So essentially, you bit pack all the arrays at the very end, but in between, you have this sort of graph of RLE delta and possibly even dictionary applied to that. And you can also think about it. So this is what we have right now, but you can also think about extending this to by replacing some of the parts. Let's say instead of bit packing, you could as easily use any other entropy encoder, and that's something we're looking into. And then again, for dictionary compression, you can maybe instead apply something like a bit shuffle that could also work pretty well. So the cascaded compressor was designed for integer data sets. Here I have some numbers. This is just for the cascaded compressor. I have some, later I'll show some more kind of detailed numbers across all the compressors that we have in NVCOMP. But you can see the results pretty nice in terms of the performance. Both compression and decompression is very efficient, like 200, 400. That's an RTX 3090. And the ratio, the ratios on the left. Here the log scale. So some of the ratios are pretty crazy, like, like 30x and like 50x and so forth. So it turned out to be a pretty good compressor for some of these analytical data sets. And then after looking at cascaded, probably about last year, me, my team, we started looking at LZ-based implementation on the GPU, and whether we can also port LZ4 or some other LZ-based compressors on the GPU. So what is LZ77? And I'm going to show you an example of LZ4. And essentially, any other LZ77-based compressors, they kind of work similarly. The difference is how they encode exactly the literals or patch copies there. So the main idea, again, is so in the LZ77, you just have some literals that you copy from the input stream, right? So like you just directly copy this APC here, and then you have another type of copies that are called match copies. So these are you copying from the previous output that you already written, and they could be interleaving. So you have some copying literals and copying matches, and then copying literals, copying matches, and so forth. Or you could have copying matches following each other. So there's a bunch of different ways you can approach that. But that's essentially kind of the core of LZ77 algorithm. And in LZ4, the way the stream is encoded, you have this token that specifies the length of the literal copy and the match copy, and then you have some additional symbols that can represent very long copies that are kind of optional, so you don't use them if the lengths are small. Then you have the literals following in your input stream. Then the offset for the match copy. Right? So you need to know from where in the previous buffer you want to copy things from, right? And then also the length that you store there, and like from where and how much you need to copy in terms of bytes. So that's essentially the core of like LZ4, the format. SNAPPY is another it's another common LZ-based compressor that's that doesn't have any entropy encoding in there. So what you can see here is that we encode the information about literals and matches, but we don't try to apply something like bit packing or Huffman to the literals themselves, right? So we store them in bytes. So it's essentially both SNAPPY and LZ4 are byte level, no entropy LZ-based compressors. And that's what we started from, because we wanted to understand. So we could do RLE, delta, and bit packing, everything, all that efficiently on a GPU. Can we do LZ4 SNAPPY efficiently on the GPU? And what we found is that it's if you just look at a single LZ stream or like LZ4 stream, it's very difficult to just map that to the GPU. And the reason is simple. If you look at the stream, you don't know when the next symbol start for your, let's say, next match copy. And even if you know that, before you decode your previous tags and literals and so forth, right? But even if you know that, you may still have dependencies for your match copies, for example. So you, the copies that you do, they depend on some previous copies, and you have this kind of loop back dependencies that's pretty difficult to implement in GPU. So it kind of serializes these copies essentially. So you could implement it on a GPU, but it's not going to work great because, again, depending on how long are your copies, what's the length of the copies, you might run easily into the just underutilizing GPU for a single stream. So the main idea is we need to chunk it. We need to chunk the data into multiple independent parts. And that sort of works fairly well with something like LZ4. So in the LZ4 standard, I think the offset length, the offset size is limited by 2 bytes. So it's essentially the maximum window you can go look back is 64 kilobyte. And that way, if you sort of use this chunking into something like 64 kilobyte, what we found is there's not much reduction in the compression ratio on the data sets that we tested. You are potentially losing some of the, in between the block dependencies, right? Like let's say from block 2 to block 1, the dictionary does not kind of extend, but what we found is it still gives you pretty good compression ratio. And in fact, many of the standard libraries like liblz4, they do have this option as well to chunk and compress each chunk in parallel. So that's the core idea. We don't want to have a single LZ stream and compress it and decompress it on a GPU. We want to chunk it into many parts, for example, 64 kilobyte, and then for each chunk apply LZ compressor. And that way, and for decompression, the same kind of thing. And then within a block, we could also use, in fact, multiple threads to cooperate. And it seems to be pretty efficient because in some cases, your match copies here or literal copies could be pretty long. And it makes sense to use your multiple threads to perform that copy. And you can also resolve dependencies. There's multiple different ways you can resolve dependencies, and I have a very detailed talk on that in GDC this year. Goes in more detail how to implement it. Okay, so we talked about cascaded, we talked about LZ, and how to parallelize it. And then one thing I want to mention, so I've been talking about the LZ decompression here, right? In fact, LZ compression is actually very interesting. It's something that I haven't seen a lot of work, publicly about on in papers on doing the LZ compression on the GPU. But I think GPU is a good fit for LZ compression, because in the compression case, your idea is you need to find the matching. You need to find what sort of what is the longest sequence from starting from that particular position that I have in the previous buffer that kind of repeats itself, right? So there's lots of different techniques how you can exactly produce the LZ stream. But I think the GPU has a good architecture for that. So if you imagine splitting the stream into 64 kilobyte chunks, then you can load these chunks into some shared memory, and then you can do a bunch of different things there to find the matches efficiently. Because you do need a lot of compute to perform these matches of the different strings within that block. So we have all that implemented in NVCOMP. We have a very efficient compressors for LZ. So let's talk about NVCOMP libraries. Once we kind of went through the cascaded and LZ, we realized, okay, there's GPU seems to be a pretty good fit for some of these compressors, and why don't we build a library? Because there's not really a core public NVIDIA supported library there, and that's how we decided, let's do one. Yeah, so we called it NVCOMP. And the goal of the library was kind of a single place where you go for lossless compression and decompression on the GPU, right? So the idea was we provide some standard interfaces that if you're a developer, it's pretty tricky to go and implement all these methods in CUDA efficiently, especially if you think about like LZ-based compression, decompression, and there's some libraries out there that are implementing some of these compression techniques. There's really no like a single place where people can go and it's supported, right? And people can use one format or another and maybe try different formats. And that was the idea. So we create a library that will have a single standard interface that CUDA developers can just use if they want to compress some data on the GPU or decompress on the GPU. So kind of like how you have CUDA memcopy, we would have some sort of like an interface that you compress and decompress. And so we released this library last year, the 1.0 in 2020. It was right about time where we, had all this research and implementation done for Cascaded, and then started looking at LZ4 and did some LZ4 implementation as well. And then we released 2.0 earlier this year. And we added a few new compressors. So we added SNAPPY, we added GDeflate and BitComp. So GDeflate and BitComp are proprietary, closed source compressors that we added, and they have their own, positioning that I'm going to talk about a bit later. But essentially, in 2.0, we had 5 compressors released, and we also added 2 different interfaces. So we realized that some people would like to handle the chunking themselves. So they have the data, they want to implement some custom chunking, and then they just want to call compress, decompress on these chunks, right? But some other people may not want to deal with the chunking. They would just want to have a simplest interface possible. So we kind of decided to split this into 2 interfaces. And I have some more slides on that later on. And then 2.1 we're working on right now. It's kind of pretty close to being released. I think we're going to release it maybe probably in a few weeks. And we're integrating it into Rapids. So now Rapids will use NVCOMP for their compression, decompression. And we also have in 2.0, we introduced some of the new interfaces, but we didn't have full support across all the compressors for them. And so now we're kind of making sure that's all supported across all compressors. We have some bug fixes and performance improvements as well. So I want to talk about the interfaces so you can see how you could use NVCOMP in your applications. And so we have two kind of sets of interfaces. One is we call low level, And that one we target advanced users. And the idea was have a very lightweight wrapper around our kernels, right? So you don't have any other dependencies or things you need to take care about. So essentially, the decompress this NVCOMP patch decompress async will just call the kernel and it doesn't really do anything else. But that means also you will, as a user, you will have to chunk your data, right, and give us these chunks, and then we'll just call, let's say LZ for compression on all of these chunks, or cascaded or something else. There's some additional APIs, aside from just like compress and decompress async calls, there's additional APIs. Some compressors need temporary memory, and the design of the library was NVCOMP is not going to allocate any memory for you. So we will tell how much memory we need, right? And you're going to allocate it on your side. I think it's similar to how something like CUB is implemented in a few other libraries. And so here I have an example. So if you need to decompress something, you will probably need to request how much temporary size the decompressor needs. Then you allocate that memory. You could also use some memory pool in this case instead of CUDA malloc, and then you run the decompression kernel. So that's kind of roughly how the structure of your code would be for the decompression. And then similarly for compression, you would sort of request how much temporary space I need, allocate that space, and run the compress async function. And so as you can see, we support batched compression, decompression. So you provide pointers to your buffers, and also the sizes of these buffers, right? And then the decompression pointers, decompression sizes, there's some that if you know them. If you don't know them, that's okay. Yeah, I'm not going to dive into the details of the API, but we can talk about that if interested. And this API is changing slightly for 2.1, by the way. So that's just some heads up. And we have, in fact, published the 2.1-dev branch with some of these changes. So you can take a look and kind of to preview what's changing in the API there. You specify a stream to say which stream you want to run this kernel. So again, it's kind of fully asynchronous, lightweight, and supports the batch compression, decompression. The only thing is you have to take care of the chunk of the data. And the second interface that we provide is a high level, which handles the chunking internally. So you don't need to worry about anything. Just give us a buffer, we'll chunk it, we'll store the metadata for chunks. And when you decompress, we're going to read that metadata and figure out how many chunks you need and so forth. So it's a kind of simpler interface. And here I have an example, and so that helps users to kind of jumpstart quickly with NVCOMP. And I have an example here of using NVCOMP together with GPU direct storage. So you could imagine something like you have a compressed file, you want to read from disk, and you could use the cuFile APIs for that to read it into the device buffer directly by passing CPU. And then you could use you create a decompressor object, you configure it, and then you allocate temporary buffer and call the decompress function. Right? So that's kind of almost the full kind of example of how we would use GPU direct storage even together with NVCOMP. Yeah, and so we're probably going to be reworking the high-level interface a little bit because we spent quite a bit of time on the 2.1 interface, 2.1 low-level interface, and make sure that works across all the compressors. I think in the next release, we're probably going to be working on making sure the high-level interface is stable and supported across all compressors as well. Okay, so let me dive into show some performance numbers, some new results, and then we cover use cases, and that's great. So I think then we can just switch to questions. So again, for methods that we support in NVCOMP 2.0, there's CASCADED that's focused on analytical, structured, kind of integer data, tabular data. There's also LZ4 and SNAPPY. Both of them are entropy encoder, no entropy in byte level encoders. And they are all, both of them are LZ77 based. pretty generic and widely used in the industry. So we decided to support them. We actually also have an example of how you could compress a file. You could compress your buffers with, let's say, LZ4, standard LZ4 library on the CPU, like libLZ4, and then you can copy these buffers to the GPU and then decompress them with NVCOMP. So we fully support these standard formats, LZ4 and SNAPPY, on the GPU. We also have these two additional methods, gdeflate and NVCOMP. So gdeflate is a proprietary compressor that has some entropy encoding there, and it gives the best compression ratios that we've seen on kind of any data. The compression ratios are similar to deflate, essentially. And BitComp is our, again, sort of proprietary compressor, but designed for floating point data. And we've seen very fast performance and good results in scientific computing applications. So here I have some numbers, ratios. I have 3 slides: ratios, compression throughput, and decompression throughput. And 2 data sets. One is columns from some tabular data set from, I think this is the same mortgage data set that I showed a few slides before for CASCADED. And then I also have a set of geometry, texture, kind of graphics data sets there that are hard to compress because they're already compressed in a way with block level kind of compression for images. And so it's kind of on top of that doing some additional compression with some, trying to check now like 2x or so compression. To highlight, kind of compare different methods. Let's look at the left chart first, I suppose. You can see CASCADED beats everything on something like column 0 and column 3, column 9. So some of the columns really work great with CASCADED, but then others like the string column works best with LZ4, because LZ4 and SNAPPY, they're both kind of targeting also strings in most cases. They're pretty generic, but they work really well on strings. And then BitComp doesn't have very good compression ratios. It's kind of, in some columns it's good on average, and like in some cases, column 7, for example, this floating point column shows the best ratio with BitComp, but it's not better across all this case. And this is actually a nice plot to look at because you can see there's no single compressor that you want to choose across all your columns, right? So it's actually important that we have all these methods, and depending on your data, depending on your, this is even like a single data set within, and like different columns from that data set, right? But imagine you have different, your own application with your own data set. You might have, you might want to use different compressors for different data. And so that's why it's important that we provide these methods within NVComp. So you can easily switch between them. It's just, they all have the same interface, and you can kind of tune for whatever compressor you want to use for your application. Then if you look at the right side, here I have hard to compress data, again, because I mentioned it's already sort of compressed with some, it's already kept, all the 2D kind of similarity is already captured by using something like block compression. But then on top of that, we're trying to extract even more. So it's really hard to compress, and you see SNAPPY. I don't even show CASCADED because CASCADED doesn't really give any compression in this case. And LZ4 and SNAPPY, about 1.4. And gdeflate works really well. It's up to 2.2 maybe. And we have like 2 different ways to compress. It's like a fast and HT. And this is essentially the same ratios as deflate for this data set. And then BitComp, it's pretty decent for geometry, as you can see here. And then for textures, it doesn't really compress things well. So now that you've seen the ratios and how it's all kind of split up, let's look at the performance and throughputs. This is compression throughput. And again, in some cases, compression matters. In some cases, it does not. because you might, maybe you're going to compress something and keep it there like on a disk or system memory for a long while, and you don't need to rerun your compression, right? But you might be just reading the data very often. So it sort of depends on the application. So some applications, they don't care about the compression throughput. Some applications do care about that. So but you're looking at the chart on the left, you see both Cascaded and BitComp, this first orange bar and the gray bar, they're pretty high up. So they both show decent compression throughput, 200, 500 on this A100 GPU. Other compressors are below that, but pretty close to each other. So like both LZ4, SNAPPY, and GD Fast, they're around 30-ish, maybe 50-ish gigabytes per second in some cases. So that's what we see for the compression throughput. And on the hard to compress data on the right, the compression throughput is probably around 10 gigabytes per second. For this, Z4 SNAPPY GD BitComp works again really well on this, and I don't show Cascaded because it doesn't really have good compression ratio. So that's the compression throughput. And decompression throughput, it's interesting. Let's look at the left chart. Now you can see, we still have Cascaded and BitComp showing great numbers here, right? It's like 200, 300, maybe up to 500 gigabytes per second. But also LZ4 decompression and works pretty well. So it's like sometimes up to 300 or more. The reason for that is in this specific case, seems like LZ4 can capture like very long match copies, and we can do very long match copies efficiently on the GPU. So just mem copy from one place to another. GD fast is also decent on some of these numbers, so it's from 100 to 200 gigabytes per second. SNAPPY is not like great, but still up to 100 in some cases. And then for this hard to compress data, you can see all these compressors work pretty well, up to 50 gigabytes per second. BitComp is, of course, beating everything, but it doesn't have as good compression throughput. And this 50 gigabyte number, you can think about it. If your data is in disk or even is in PCI-E, for example, also sorry, in CPU memory, you're going to be copying over PCI-E, and let's say we have about 2x compression ratio. So this throughput is measured as the decompressed size divided by time. So if you convert it to like a decompression throughput based on the compressed size, right? Then it will be like half of that, so like 25 gigabytes per second. So essentially, it's kind of matching whatever your PCI-E bandwidth is. So you can copy the data at PCI-E bandwidth in compressed format and then decompress in parallel, right, at the same time, and fully hide the cost of decompression or the cost of copying there. So yeah, these numbers are pretty impressive, and yeah, I think that's all for the numbers. Maybe I can move to use cases, highlight a few things here. I mentioned that Rapids, they have a bunch of different file readers, and we use Rapids to accelerate some of the data analytics and database queries on the GPU. The whole idea, you read some files, you need to parse them, convert them to columns, and then perform some database operations on these columns. That could be a join or group by or something else. And what we found is in many of the real world queries, the time to actually get the data in, but then decompress the data and kind of convert the data to columns, kind of parse this data is we spend a lot of time on it. And so this is an example pie chart here, like how much time we spend in different kernels in a typical query. And often like 50% of the time or so spent in these decompression kernels. So it's a big bottleneck in Rapids, and that's what we focused on from the start. And again, in this case, it's important to support all the standard formats, because you don't sometimes you don't have a choice to store the data in a different format, and a customer has some files in, let's say, in LZ4, maybe a Parquet file with LZ4 compressed pages. So you have to support LZ4, and being able to move this, a set of pages to the GPU and then decompress this, pages on the GPU. That's what we're kind of doing in NVCOMP. So it's a good fit there. The other use case is accelerating communications. So when you have very fast compressor and decompressor, that enables a whole new thing for if you're something like InfiniBand limit, InfiniBand bandwidth limited or Ethernet bandwidth limited. On the left, I have a chart here that shows an example. Depending, so if you just send the data, raw data over 200 gigabit NIC, right? And now imagine if you want to compress, if you have a way to compress your data fast and then send less data over NIC, right? And then decompress on another end. And so I show roughly, depending on the compression ratio and the combined throughput of your compression decompression, what kind of speed up can you achieve over just sending raw data over NIC. And you can see here, so if you have something like, let's say, 8x compression ratio and then 200 gigabytes per second compression decompression speed, then you're looking at a 3 to 6x improvement for your end-to-end communication. So that's like comparing sending a raw data in a bandwidth limited regime versus compressing versus account for compressing, sending the less data and then decompressing. And then for that, with compression approach, you will get a 3 to 6x speed up over the sending raw data. And so we actually did that for one of the database use cases and like applications. So we published recently a paper at ADMS. The idea was to let's look at implementing a join on 1,000 GPUs. And in that scenario, you're most likely limited by sending the chunks from one GPU to another. So it's all-to-all kind of communication bandwidth limited. And we used the same cascaded compressor, decompressor that I mentioned previously. And we managed to get the end-to-end speed up for the distributed join up to 2x with compression. So that was a pretty interesting result. So like without compression, you're limited by your network speed, but then you could also apply compression and improve the throughput by about 2x end-to-end. And in this use case, comparing to the previous one that I showed, you have a flexibility which compressor you want to use, right? So you could use a cascaded, you could use something else because it doesn't matter as long as you can compress and decompress fast. On the other end, it doesn't really matter. You're not like tied to a specific compressor. Compared to in this case, you have your files in critical formats, so there's no you have to support it. And the other use case I want to show, it's similar to the previous one, but in Spark, during shuffle, the data is also compressed, and then the way it works, it could be also sent to a different GPU, or it could be stored on disk or system memory. And by default, I think Spark is using LZ4, but it's configurable, so you can, in principle, use any other compressor. That's another potential use case for NVCOMP. And the last use case I want to highlight is in graphics. Today's games are getting more sophisticated, right? You have large scenes with lots of textures, with geometry textures, all kind of streaming, bulk loading of these large scenes as well. And so because of that, many so modern games, they just store all the assets in compressed format, in fact. And if you have that, then if you need to render like a scene with some geometry and texture, you need to then send this data over, right, to the GPU, and you need to decompress it. And in the standard pipeline, you would send it to the CPU, decompress on the CPU, send data then in the uncompressed format to the GPU. So the PCI-E is heavily utilized, and you will be sending also the uncompressed data over PCI-E, not quite efficient. You will also be using lots of CPU power to just do this decompression. But if you have a fast and efficient GPU decompression, you could do the whole process on the GPU, and you also use less PCI-E. Now you just need to send compressed data once, and then you can do decompression on the GPU, and that could be very efficient. There's a link at the bottom here, a bit more about that technology, but essentially kind of the same idea as I mentioned. And the chart on the right shows how many roughly CPU cores you need to achieve to fully saturate sending the compressed stream from SSD. And you can see it's a lot of CPU power that will be burned if you want to do decompression on the CPU. Yeah, I think that's all. I just wanted some few things I want to show as a takeaway. I think we went through different algorithms on the GPU for compression, decompression. I think the architecture of GPU is a really good fit for compression specifically, and for the decompression as well. We showed pretty good performance. And now sometimes it's very tricky to implement these algorithms though, because of the lots of dependencies and encoding, decoding, and different methods. But now we have this library that just gives CUDA developers access to all these methods and fast implementations and through a single interface. And then the second thing I want to mention is if you can think about ways to leverage compression in your applications, I'll be interested to hear your use cases. And I've showed a few examples, but I'm sure there's lots more. So I think this is a kind of growing field, like in terms of how can you use compression, like fast and efficient compression for different types of applications like that. The other day, I talked to somebody and they mentioned to me you could use it for like a normal, sort of like an image similarity problem. You could express it in a compressed kind of representation, so you can compute the distance between two images by showing like if you compress them at the compute symmetric there. I think it's called like NCD or something. So it is like one other interesting use case for compression in kind of unrelated topic of like image similarity or something. So yeah, think about applications and how you can leverage compression. Maybe you can come up with like, okay, now if I have a fast, efficient compressor, how can I use it? And maybe I can rewrite my application and make it efficient through that. And then the third thing is, yeah, try NVCOMP and let us know any feedback. It's still very much a project. I wouldn't say it's a product yet. So we have lots of ideas. We're kind of shaping out the new interfaces, new methods, and yeah, if you have some ideas who want to contribute or report an issue, that's all very welcome. Yeah, I think that's it. And you can see it's a lot of CPU power that will be burned if you want to do decompression on the CPU. Yeah, I think that's all. I just wanted some few things I want to show as a takeaway. I think we went through different algorithms on the GPU for compression, decompression. I think the architecture of GPU is a really good fit for compression specifically, and for the decompression as well. We showed pretty good performance. And now sometimes it's very tricky to implement these algorithms though, because of the lots of dependencies and encoding, decoding, and different methods. But now we have this library that just gives CUDA developers access to all these methods and fast implementations and through a single interface. And then the second thing I want to mention is if you can think about ways to leverage compression in your applications, I'll be interested to hear your use cases. And I've showed a few examples, but I'm sure there's lots more. So I think this is a kind of growing field, like in terms of how can you use compression, like fast and efficient compression for different types of applications like that. The other day, I talked to somebody and they mentioned to me you could use it for like a normal, sort of like an image similarity problem. You could express it in a compressed kind of representation, so you can compute the distance between two images by showing like if you compress them at the compute symmetric there. I think it's called like NCD or something. So it is like one other interesting use case for compression in kind of unrelated topic of like image similarity or something. So yeah, think about applications and how you can leverage compression. Maybe you can come up with like, okay, now if I have a fast, efficient compressor, how can I use it? And maybe I can rewrite my application and make it efficient through that. And then the third thing is, yeah, try NVCOMP and let us know any feedback. It's still very much a project. I wouldn't say it's a product yet. So we have lots of ideas. We're kind of shaping out the new interfaces, new methods, and yeah, if you have some ideas who want to contribute or report an issue, that's all very welcome. Yeah, I think that's it.